Hello and welcome to Autology, the podcast that brings you the latest insights into automotive technology. I'm your host, Matthew Beecham, Research Manager here at S&P Global Mobility. In today's episode, we're really excited to have Mengyin Tao, Principal Research Analyst for Materials at S&P Global Mobility, and Ingo Olschewski, who is Director of WorldAutoSteel, a group of the largest automotive steel producers focused on advanced automakers' use of steel for future mobility. Today, we're going to chat about something that's super important in the automotive world, advanced high-strength steels, or AHSS for short. With the industry making a big shift towards electrification and sustainability, these materials are becoming key players on how cars are designed and built. We'll explore how these advanced high-strength steels are not just about safety, but also about making vehicles lighter and more efficient. It's a fascinating time for automotive innovation, and I'm looking forward to hearing Mengyin and Ingo's insights on the trends and challenges in this space. So a very warm welcome to Mengyin and Ingo. It's great to have you here.
So hello, also Matthew from my side, Ingo speaking. I really appreciate to be part of this podcast.
Thank you very much. You're very welcome.
Hello, everyone. My name is Mengyin. I'm really happy to join today's session. I'm a principal analyst for S&P Global Mobility. Thank you very much to join us.
Thank you, Mengyin. You're very welcome. As we dive into this topic, it's clear that advanced high-strength steels are becoming increasingly important in the automotive landscape, especially with the rise of electrified vehicles. So let's kick things off with a big question for you, Ingo. How do you think advanced high-strength steel will play a more important role in the electrified vehicles? And what do you see as the greatest opportunities and challenges for automotive steels in this new era?
Yeah, Matthew, thank you very much for this first big question. I think if we strongly address characteristics like strength, lightweighting, cost, and safety more than ever, so that advanced high-strength steels are becoming even more important in an EV world. So what we see right now, or also for the last years, where we deal with electric mobility, is that the key technology in every electric vehicle is the battery. And the battery mass makes lightweighting more critical. Electric vehicle batteries add approximately 180 to 320 kilograms to a vehicle. So to maintain range and performance, the automotive OEM must reduce the overall weight of their vehicles. And here, advanced high-strength steel provides a high strength to weight performance at lower cost than other materials. And also, safety requirements will steadily increase in the future. Electric vehicle architectures must protect the battery pack from crash intrusion. And this raises performance demands towards side impact beams and rockers, reinforced force structures, stronger pillars, and load path. Advanced high-strength steel is uniquely suited to create predictable crash energy management with engineered ductility. Another option in electric mobility or in electric vehicles is the thermal management and the battery enclosures. The requirements here are high stiffness, fire resistance, crash containment, compatibility with joining and sealing systems. So steel, and especially advanced high-strength steels and coated steels, offers advantages in nearly all of those points. So steel performs much better in battery fire and thermal runaway events. But this can also turn into a challenge in the future, because with new cell chemistries on the horizon, like a possible change from liquid to solid-state batteries, which might have a lower fire risk or fewer thermal runaway. And we as a steel industry must investigate how we can contribute on this change. And therefore, we will start with a strategic study from 2026 onwards to approach this topic. Finally, what we see in this game of electrification is that the overall cost pressure in electric vehicles is still very high. We are still some way off from the point that affordable electric vehicles become a mass phenomenon. And in this context, batteries already dominate the cost structure of electric vehicles. So OEM are aggressively cost reducing every other system in the vehicle. Compared to other materials, steel is cheaper to produce and repair. It uses existing stamping, welding, and assembly infrastructure and has higher recycling value and lower embodied carbon. So as a key takeaway from this section, we believe that advanced high-strength steel are well positioned to become more, not less relevant in an electrified future, especially as OEMs push for sustainability, reliability, and lower costs.
Thanks very much, Ingo. That's a really great introduction. Mengyin, this might be a nice segue to bring you in to ask for your independent view on this area and perhaps share some research insights from S&P Global Mobility.
Thanks, Matthew, for this question. From my end, I see electrification is an inevitable trend in the automotive industries all over the world. Undoubtedly, at present, China moves very fast to embrace electrification. And though in this year, major countries in Europe region and North America region have somewhat reframed the timeline and pathways to meet the CO2 emission target. But eventually, the goal of stopping the climate change will not be changed. So the electrification is, again, the inevitable trend all over the world. According to S&P Global Mobility's forecast, in 2032, pure electric vehicles share in all new vehicle productions is expected to surpass 50% in Europe and the Greater China region, and 35% in North America. There are other types of electrified vehicle, including the plug-in hybrid, full hybrid, REX, etc. All of these will fundamentally change the landscape of the auto market that has been dominated by petrol and diesel vehicles for a long time. As far as the gross vehicle weight is concerned, which is the topic of today's session, electrification is imposing great challenges on the materials adoption for structural components as well as exterior closure parts, for which engineers are seeking new solutions to make the best performance to the lightest weight. In this way, large capacities batteries, smart and intelligent devices, and more sensors, controllers, all of these smart things that enable the highly automated driving features could be installed on the vehicles without violating the gross mass limits of the car, which ensure the proper handling properties of the vehicle. On the other hand, stringent requirements on passive safety have placed the material selection as one of the most crucial elements in cost design. For an electrified vehicles, when unexpected collision happens, not only the driver and passengers need to be well protected from injury, but the battery must be firmly secured in place and avoid being squeezed or deformed, which may trigger the chemical reaction inside the battery and lead to thermal instability. Moreover, the fundamental structural design of electrified vehicle differs from the conventional ones with combustion engines in many places. Here I would like to show one example. It is expected to have a fully flat underbody to carry a large battery in one piece. And it is expected to have a relatively low step height to entering the car cabin that lead to so-called cell-to-chassis or cell-to-body design, both of which have to transform the central tunnel reinforcement and the cross members into the other form, which require the support of the new materials to secure the proper material properties. So all of this change could only be achieved with the adoption of the advanced steels. High-strength steel is not only a single type, but a large group of diversified steel materials. Generally speaking, applications of high-strength steels enable flexibilities in part design and may provide the best performance to the best cost.
Very interesting. Thanks very much, Mengyin. That's really, really most enlightening. You know, When we talk about body and white structures, aluminium casting has really taken the spotlight lately. It's great for integrating those smaller parts and simplifying production, but I'm wondering if you think we could achieve a similar level of parts integration using these advanced high-strength steels. Ingo, what are your thoughts on that?
Important question, Matthew. And to answer this question, we have to broaden the perspective a little bit from the level of the materials to the level of the OEM requirements. The most important OEM points, right, the OEM pain points right now is to optimize the tension between complexity, cost, and time to market. And therefore, OEMs are attracted to aluminum megacastings because they reduce complexity in their overall processes. Fewer parts, fewer welds, fewer robots, shorter assembly lines, even if the casting itself is more expensive. So what's in it for steel? Steel solutions cannot directly replicate aluminum's large casting approach, but steel has its own integration pathways that, when combined, can match or surpass the cost, weight, complexity, performance of castings for body in whites. The key issue is using smart and intelligent parts integration. And here I would like to give you two examples. Tailor-welded blanks or tailor-rolled blanks are one of steel's strongest answers to parts consolidation. This means the combination of multiple thicknesses and strengths in a single stamp component can reduce 3 to 8 conventional parts down to 1. It also enables local reinforcement exactly where needed. And the result is fewer tools, fewer welds, lower assembly complexity. Another example are hot stamping, let's call it mega shells. Hot stamping enables shapes normally impossible with cold-formed advanced high-strength steels. They have an extremely high strength, a deep drawability, and their complex geometry allows consolidation. So actually, some OEMs already use large press-hardened steel shells that replace Templar stamp piece parts. Generally, the steel integration can match with aluminum megacast benefits in terms of cost reduction, meaning that steel's integration methods require far less capex than megacastings. Here we see that no massive gigapress, no enhanced foundry infrastructure or thermal management systems are needed, and existing stamping lines can be reused. Another point is repairability. Megacastings are difficult and often impossible to repair economically. Steel modules remain repairable with conventional body shop techniques. Also, crash performance is another important factor. Steel's energy absorption per kilogram outperforms other materials. With tailored thicknesses and advanced high-strength steel, load path can be precisely tuned. So wrapping it up, steel can achieve highly equivalent system-level benefits compared to aluminum megacastings through a combination of tailor-welded blanks, hot stamping, laser welding, modular design, mixed materials where needed, which achieves most of the value without the challenges of aluminum castings.
Very clear indeed. Thanks very much, Ingo. That makes a very compelling case for steel's integration pathways. Mengyin, what's your assessment on this, please?
Okay, thanks for the question. Nowadays, I think unibody car body design is still very popular all over the world. This unibody car body featured with the structural part in underbody section and solid skeleton architecture for the upper body section. The underbody section is responsible for not only transferring the loads, but also for being able to resist deflections, while the upper body design is very important for occupant safeties when collision happens. As casting parts inherently have higher static stiffness than stamped and joined ones, aluminum gigacasting have been primarily prioritized towards the production of the structural part in the car, particularly for the underbody section. Motivated by the trend of the automotive electrification, as we just addressed just now, as well as the evolution of the lightweighting designs, aluminum jigger casting has been proved as an effective way to increase the aluminum's usage in a car for the sake of reducing the gross weight of the car body or the gross weight of the vehicle. Single material and uniform gauge casting part can eliminate complex joint, improving the structural integrity and elevate the body shop's operation efficiency and optimize the layout in the plant floor areas. But on the other side, we see aluminum jigger casting are still facing significant key challenges. It requires very high upfront investment for the machine and the toolings setup, as well as peripheral devices. And it normally has a high scrappage rate during the production phase and substandard quality of the finished part due to porosity and the use of heat treatment-free material. And as just now Ingo has already pointed out, repairing the large casting after accident can be very challenging or impossible, and it gives actual burdens to the end users. So these are all challenges stop aluminum jigger casting from gain more market shares nowadays. But on the other ways, we will pursue the part integration. But part integration with AHSS can be more diversified and be used in many places in car body. And here I can give you some example of this part integration with AHSS from the engineering practice I see in my home country, Great China. We see that BYD and other Chinese OEM use tailored roll blank to build the longitudinal rails and the battery cases as a cost-efficient way to meet the very high standard and also to make the part very cheap. And to use the tailor-rolled blank can be cold forming, and also the hot forming process can be leveraged to make the final part. Secondly, hot forming is widely used in China and global. Hot forming helps to reduce the number of the child parts to integrate as many as child parts into one piece. For example, the door ring is composed of a different grade of high-strength steels in various gauge, and the laser welding technique is used to stitch them as an integral part, and the conventional stamping process forms the integral part eventually. Part integration with AHS can enable different strength performance in different locations, while allowing thinner gauges. There are complete supply chains, which include steel makers, tier 1 suppliers, and OEM body shop in major automotive production regions, all of which can help to extend applications of such solution.
That's great, Mengyin. Thanks very much for that. There's a very interesting examples there, very clarity, but great some examples of BYD and other Chinese OEMs using these tailored roll blanks. Besides car bodies, though, Ingo, how do you see if the lightweight trend will also benefit advanced high-strength steels to be more used in other systems of the car, such as chassis or interior structures?
Yeah, that's also a good question. And also here, we have to have this holistic view on the vehicle itself and not only on one specific domain, because at the end it counts that we have a efficient vehicle as a whole and not just in one domain. And therefore, the lightweighting trend in electrified and highly efficient vehicle is opening new opportunities for advanced high-strength steel outside the traditional body in white. especially as OEMs are trying to counteract battery, as we already addressed before, battery mass without dramatically increasing cost in other domains. And one domain which is important, or which is interesting, is the chassis system, where electrification is changing the load demands. So we see opportunities for advanced high-strength steel, for example, in suspension components. Here, especially in control arms or stabilizer bar brackets, or in subframe components. And talking about electric vehicle subframes, this is a very, very crucial point, because they must manage battery mass, they must manage higher torque output from electric motors, and NVH tuning with fewer powertrain isolation points. And here, advanced high-strength steel can play as an enabler with lightweight hollow members, closed section geometry via roll forming and hydroforming, or tailored thicknesses for crash load pad. And another domain that we see are, for example, seating structures. Seats are moving towards thinner profiles, integrated safety elements, and heavier electronics, with all the features right now you see in the seats, from heating and so on. The advanced high-strength steel adoption here includes ultra high-strength steel seat frames or press-hardened steel beams. The benefits, they are clear. So the benefits are mass reduction, higher stiffness for dynamic comfort, and better side impact protection. And also we see potential in the underbody and thermal systems. Advanced high-strength steel is gaining traction here in motor housings and shields, thermal protection components, or underbody closures. Because electric vehicles require more thermal protection between battery, motor, and cabin. And here, advanced high-strength steel offers fire resistance, heat shielding, and formability for complex shapes. So overall, advanced high-strength steel has the potential really to further penetrate in these key areas, because they provide lightweighting at low cost, high crash performance and stiffness, compatibility with existing tooling, and sustainability, as well as recyclability. Steel will not replace alternative materials everywhere, but its share will grow across multiple systems where costs, safety, and manufacturability outweigh absolute mass reduction.
Super. Thanks very much, Ingo. There's a lot going on in far more areas than one would think. Mengyin, I'd like to get your thoughts on this one, if I may. Since advanced high-strength steels and aluminium alloys are most probably used in battery to make battery cases of the electric vehicles, how do you think the market competition for these two groups of materials for this single large component? Will advanced high-strength steels have a chance to win more market share by 2030, do you think?
Okay, indeed, battery case is a very important part for the electrified vehicle, and the battery case itself is normally consisted of main frame, upper cover, lower cover, and cross members, which split compartment to accommodate cells and modules. Generally speaking, a mixed material solution is mainstream to make the battery case nowadays. As far as the main frame of the battery case is concerned, high-strength steels and aluminum contribute to different strategies of the structural design for most of the OEMs. Some OEM would prefer one material solution over another, and some other OEMs would choose another materials. For example, I can give you some example to show what I just mean. General Motors Arteon platform adopted a full steel solution that features the use of 1,500 megapascal steel to make the main frame of the battery case. Similar design and material adoption strategy could be seen on last generation of the Toyota's BZ4X, which is a pure electric vehicle, where roll forming component from a dual-phase steel with 980 megapascal tensile strength are used. So as OEM in Korea, like Hyundai, Kia, also use the advanced high-strength steels for battery protection structure. At Tier 1 supply end, we see that Benteler, Magna, Baosteel, and ArcelorMittal continue to work out new ideas with advanced steels on this part. But on the other end, I would say Chinese OEMs are now more in favor of the battery case made from the aluminums from traditional automakers like BYD, Geely, to startup companies NIO, Li Auto, Xpeng, as well as Volkswagen's MEV platform. Their solutions for the battery case, the material adoption strategies are similar, which is aluminum extrusion frame plus die casting cross members. With regard to the future trend, I would like to shed a little bit light on this. I think we might need to go back to the comparison of the material properties. We know that for aluminum, it is lighter than steels, and it can be extruded, cast, or stamped into complex shapes. For the battery case, using the aluminum extrusion can enable integrated cooling channels inside the battery case and lightweighting structural designs. However, advanced high-strength steel has its unique advantages, like it provides excellent torsional stiffness, ensuring the vehicle to maintain the structural integrity. Also, advanced high-strength steel is significantly cheaper than aluminums. Also, advanced steel supply chain are more mature and reliable. It can support mass market electrified vehicles program. Eventually, I think we can at present we can expect the evolution of the material adoption for this component to go parallel into two ways. The one is more and more use of the press hardened steel from the hot stamping process, which secure very high strength of the structure of the battery case. And the other very promising way to build the battery case in the future is one piece from the large gigacasting machine. But to use the aluminum gigacasting to build this very large battery case would use a very high and very large machinery whose clamping force might exceed, to my understanding, 9,000 metric ton. But I think these two future trend would be worth of further observations from our end.
Thank you very much, Mengyin. That's very comprehensive, really useful, and a very interesting comparison of material properties there. One other thing a couple of other things I'd like to go through, if I may. Since steel is still the go-to material in most vehicles, I'm just curious about how automotive steels can really shine when it comes to sustainability. Ingo, what do you think are the competitive advantages of steel in meeting those sustainability goals, like life cycle assessment and carbon emissions?
Yes, sustainability also a very, very important point. Sustainability is the responsibility of us all on a societal level. And what we see here is that automotive steels are in a very strong position. Also now coming back to the automotive industry, as OEMs increasingly shift their competitiveness metrics from pure mass reduction to sustainability, cost, and quality. A sustainability goal tighten, or the sustainability goals tighten really globally, and steel gains more structural advantages against other materials from that. So looking at life cycle assessment, for example, the automotive industry is moving away from mass reduction at all costs and towards CO2 per functional unit. When using LCA instead of mass-only thinking, steel can outperform other materials in most structural applications. Just two examples for that. Primary aluminum production has a higher CO2 intensity than steel. Carbon fiber and polymers have even higher embodied CO2 and a really difficult recycling processes. So steel can already be produced with low carbon pathways that sharply reduce upstream emissions. So OEMs can meet sustainability targets more cheaply by redesigning with low carbon steel rather than substituting to energy intensive materials. OEMs are now scoring materials not just by CO2, but also by scrap recovery rate, closed loop feasibility, and recycled content availability. So steel can provide crucial benefits to all of these three topics. And I think overall sustainability should also enable cost competitiveness, not just environmental compliance. And in this context, steel uses existing stamping, welding, and repair infrastructure. Green steel routes become cheaper over time, and carbon taxes and border adjustment mechanisms penalized high CO2 materials. So for this section, for me, the key takeaway here is sustainability is turning into one of steel's strongest competitive weapons. As sustainability becomes a purchasing criterion, automotive steel shifts from a more, and this is really important, from a more cost material to a strategic material.
Thanks very much. Thanks very much indeed, Ingo. That's some great and clear messages there. Very important ones too. Thank you. In the long run, we can expect highly automated or even fully autonomous driving vehicles to be on our roads around the world. How do you think that shift will influence material choices for the structural parts of those cars? Mengyin, could you start us off on that one, please?
Yes, I would like to. Ideally, autonomous driving will definitely reduce the frequency of the crash accident. But passive safety remains very essential since mixed traffic conditions will persist for years. Here I mean the autonomous driving plus the human drives on the road. And in any scenario, crash accidents are really hard to be avoided after all. According to S&P Global Mobility's forecast, strong demands for autonomous driving, here means level 3 and above, will start to emerge on the public road in all major automotive regions after 2026. Market shares of the highly automated vehicles in each region will rapidly grow in the next decade. Autonomous driving might bring about different crash scenarios, which need redesign of the passive safety mechanism in a car. And here, I would say advanced high-strength steel will play a very important role again. And this is a very simple thought from my end. And I would give the ball back to Matthew and Ingo to share some of your insight on this topic.
That's great, Mengyin. Thanks very much indeed. Ingo, what's your take on this? Given this shift?
Yeah, thanks very much. I would like to jump in here. What we see is that the shift towards these high automation and full autonomy will change the engineering priorities of future vehicles. And yeah, those priorities will directly influence material selection for structural parts. And the changes are not just incremental. What we see right now is that they reshape how bodies, chassis and interiors are designed. So let me quickly run through the most crucial points. The first point is that autonomous vehicles need higher structural rigidity and tighter tolerances to ensure sensor accuracy. In this context, the vehicle body must maintain highly stable mounting positions, minimal deformation under load, thermal cycles, or vibration. And the long-term dimensional stability must be secured over millions of miles. And so the implication is that materials with high stiffness, low creep, predictable deformation, and good thermal stability become more and more important. And as autonomous systems demand precision-grade structures, steel becomes favored for roof rails, A and B pillars, cross-car beams, or subframes. Another point is that continuous operation and fleet usage increases the durability requirements characterized by the high mileage, the high utilization factor, and commercial assets. This increases the emphasis on fatigue strength, on corrosion resistance, on long-term durability, on low repair cost or structural redundancy. And finally, this is also what Mengyin already addressed. What we see is that autonomous vehicles, likely they will reduce crash frequency, but still we will drive for a lot of decades in mixed traffic. So we will have crashes, and those vehicles must exceed current safety performance. So also here we don't see any hints on reductions in safety regulations or something, because even if AVs crash less frequently, but when they do, the liability is enormous. OEMs and fleet operators will therefore focus on the crash absorption, the battery protection, the occupant protection in unconventional seating layouts, and protection during autonomy system failures. So that this drives stronger materials in rocker panels, battery enclosures, side structures, or roof structures. Autonomous vehicles may reduce external crash loads, but the cost of failure increases, favoring robust and reliable steel solutions. For us here, the key takeaway is that overall, the advanced high-strength steel will be essential in future autonomous vehicle architectures. Autonomous vehicles make steel even more strategically important because they demand a combination of structural precision, high stiffness and safety, durability, sustainability, low cost, as well as repairability.
Thanks very much, Ingo. Yeah, there's some really interesting points there around about the steel and the crash and crumple zones and so on. Very enlightening. Can I stick with you, Ingo, for a moment? I'm wondering if WorldAutoSteel has looked into the idea of using full advanced high-strength steel body for a vehicle designed without a human driver. And if so, what advantages might advanced high-strength steels bring to a concept like that?
Yes, thanks. This I can connect perfectly with the arguments I put on the table in the last section. So yes, WorldAutoSteel has already explored the concept of a full advanced high-strength steel body for autonomous, respectively non-human driver vehicles. And we strongly suggest that advanced high-strength steel is not only viable, but strategically advantageous for this type of vehicle. Our own concept vehicle, which is called Steel Motive, which was launched in 2023, directly addresses this scenario. And just let me quickly point out what the Steel Motive was designed for. It was designed for urban mobility as a service or driving in an urban mobility as a service scenario, like, for example, robot taxis with fully electric operation and high utilization vehicle cycles. And within this Steel Motive concept, we used extensively advanced high-strength steel for the body in white, with nearly 50% of ultra-high-strength steel, tailor-welded and tailor-rolled blanks, and it has an optimized crash structure for driverless vehicles. And, of course, its structural efficiency allows cost reduction potential. And the advantages here of using advanced high-strength steel in an autonomous vehicle like the Steelimotive play an important role in the following points that I would like to bring on the table. For example, sensors require extremely high stiffness for precise and reliable detection. The crashworthiness becomes even more important in commercial robot taxis. For example, Steelimotive specifically achieved excellent crash performance using advanced high-strength steel thicker gauge components. Fleet vehicles need extremely long life cycles. Here, the advantage for steel in durability costs is crucial for robot taxis. Advanced high-strength steel is a highly economical structural material, and advanced high-strength steel offers potential for new body architectures, with, for example, alternative door or entry concepts. So, well, yes, to answer that question again, yes, WorldAutoSteel has already explored and demonstrated the potential of a fully advanced high-strength steel-based structures for autonomous vehicles through Steelimotive. And the results strongly support the idea that an all advanced high-strength steel body should be highly considered for level 4 to level 5 driverless vehicles. Because in many ways, I think advanced high-strength steel aligns perfectly with the core engineering economic needs of autonomous mobility. Precision, rigidity, safety, durability, sustainability, scalability, and cost effectiveness.
Very interesting, Ingo. Thanks very much indeed. I think we've just got time for one more question, if I may. Mengyin, can I run this one past you? As we're seeing more focus on keeping the passenger cabin safe, I'd be interested to hear about the latest advancements in using advanced high-strength steel and some of the innovative fabrication processes out there. How are these developments meeting the needs of the end users, would you say?
Okay, thanks for the question, Matthew. And for the sake of saving some time, I would like to be concise in my answer. And here for this question, I would say door rings and hydroforming are two distinguished cases. I would like to introduce to show the latest advancement in using the advanced high-strength steels. And these are some innovative things to be widely used nowadays in automotive industry. First of all, door ring technologies has been incorporated into a standard safety topology. It is integral in all kinds of vehicles. The door ring technology creates a stiff load pass cage for occupant protection in side and frontal impact event. Tailoring steel strengths supports the energy absorptions in key roles, while some other tailor-welded blank can combine the very strengths to make the whole part stronger in safety room and lighter elsewhere. And Chinese OEMs are again in favor of the door ring technologies. And at present, as we can see, including BYD and the Geely Group are using the integral front and rear door rings made from up to 2,000 megapascal press hardened steels for its high-end vehicle models. And also for some other OEMs, they are using the door rings by stitching different kind of high-strength steels that consist of 918 megapascal ultra-high-strength steels to even 1,300 megapascal martensite steels to create the door ring structure for the mid-class or entry-class vehicle models. The second thing I would like to introduce is hydroforming technology. And we see that it is another proven technologies for OEMs who aims to balance the high crush performance with lighter and more efficient manufacturing endeavors. And hydroformings can replace multiple stamped and assembled part with a single and complex component. It allows the complex shape with concavities to be formed, as well as transformed different sections along the length of the tube, which would be difficult or impossible with conventional standard stamping. And all in all, it contributes to the lighter weight but stronger in the stiffness. And also hydroforming allow a wide spectrum of raw material from the second generation of the high-strength steel, trip steel, dual-phase steels, to the martensite steels, of which the ultimate tensile strength of which could be above 1,500 megapascal. In not only in China, but also the global OEMs are using this hydroforming process to make the structural part for their car body. For example, Ford used the hydroforming A-pillars on its C2 platform, enhancing the load distribution to the windshield header and hinge pillar. Also, Nissan used the hydroformed door to roof support to achieve 25% strength boost with a thinner gauge. And we can look forward to more advanced high-strength steels usage in car body design in the next few years. And I think stay tuned with us, and I can bring you more cases of such engineering practice in the major automotive countries.
Stay tuned, we will. Thank you very much indeed, Mengyin. And unfortunately, that's all we have time for today. So a very big thank you to you both for joining Autology.
Yeah, thank you very much. Thank you very much again. Appreciate that I could have been a part of this podcast.
Thank you.
Thank you very much, and really happy to join today's session, and really appreciate to talk too much with all of you guys.
Thank you very much,
Thank you.
Mengyin. And thank you all to all you listeners for tuning in as well. We'd love to hear your thoughts on today's episode at our autology@spglobal.com email, and you can find out much more at autotechinsight.spglobal.com. And don't forget to hit all the subscribe, follow and like buttons to stay on track with the latest Autology podcasts. And we very much look forward to you joining us again in the next episode. Bye for now.